I can start. Is it 1 hour including West?
Okay, sure. Good afternoon, everyone. Welcome to my talk. Today I'll talk about Fathom, which is a browser-based network measurement platform. My name is Mohan, and this work is a joint collaboration between collaborators from UC Berkeley, CNRS and UPMC, and ICSI Berkeley. Now, in this age of user-centric computing, end users can access their personalized web content from any location or device. Now, this has a major implication that the number of end host devices has increased significantly. In other words, the edge of the internet has become much more crowded now. Now, network measurement from the perspective of the end host is vital for both researchers as well as practitioners. Researchers would like to understand and gain an insight into how the internet develops at the edge, while practitioners would like to solve individual performance problems. So in recent years, there has been a considerable interest in the research community in developing such user-centric measurement toolkits. A few of the recent ones are listed on the slide. Now, such softwares are either standalone softwares or they are built as either extensions or plugins to existing or pre-installed softwares. For example, Dasu is a popular BitTorrent, it's an extension to a popular BitTorrent client, while HostView is a native application which requires users to install it with elevated privileges. And similarly, browser-based speed tests are essentially Flash applications which run on top of the Flash runtime. Now we have so many different kinds of measurement toolkits which require different and competing platforms to work on. Now all this creates a large amount of overhead for both the end users as well as the researchers. Now this overhead is compounded by the fact that security researchers have found out a large number of vulnerabilities in both the Java and the Flash runtimes. In light of this, both Microsoft and Apple have decided not to pre-install Java in their upcoming versions of operating systems, and further Flash is being slowly phased out in favor of HTML5. Now as end users, we would like to have a system where we don't have to worry about our security and privacy, while as researchers we would like to opt for a system and we don't have to worry too much about platform specifics. So therefore we thought, is there a better way to build a network measurement platform? And the answer is yes. The web browser presents an excellent opportunity to build such a platform. And there are two main reasons for this. First, the web browser is ubiquitous. It's available on devices of all form factors now. And secondly, it's one of the most popular programs ever, and therefore it's available all the time. But the web browser was not designed originally from the point of end host measurements, and therefore there is no real measurement API within the web browser as of today. And also the current security model does not protect the end host from security sensitive measurements that might be performed on the client. So I now present to you Fathom, which is a practical browser-based network measurement platform which provides a programmable interface for launching and writing experiments from the convenience of your web pages. Fathom leverages the ubiquity of the web browsers to allow unparalleled access to the internet edge. It allows novel analyses by supporting both passive and active measurements on the end host, and it combines existing security primitives to enhance the security and privacy of the end user in performing end host measurements. Now this is the outline of my talk. I'll first describe a concrete example to demonstrate how building a network measurement platform within a web browser is a good idea and has its merits. I'll then touch upon Fathom's design, specifically discussing the nature of the APIs that it supports and the set of security primitives that we provide. I'll then discuss Fathom's implementation in a real web browser. Next, I'll discuss Fathom's evaluation, touching upon the overhead and accuracy of its measurements and several case studies that we've performed with Fathom. And lastly, I'll conclude. Now, Google Maps is a hugely popular web application with thousands of users daily. We went to the Google Maps forum and saw that a large number of users had a common complaint that the web application loads very slowly. This slide shows one such comment, and in response to such comments, a Google employee volunteered to help, and he posted a bunch of questions that he wanted the users to answer in order to assist them. Basically, the questions were like this. Since when was the user facing this problem of slowdown of the Google Maps web application? Can the user quantify the nature of the slowness? Was it in the order of seconds, in the order of tens of seconds? What was the system load when the user observed the slow web application? Basically, what was the CPU and the network usage? And lastly, can the user give a metro level granularity of the location where he is situated when he observed the problem? Now, for an end user or a lay user, answering all these questions precisely and accurately is a hard job. Moreover, if the user is able to answer such questions, the turnaround time for any kind of assistance is usually in the order of days or weeks, and therefore clearly this is an inefficient solution. Now, wouldn't it be nice if the web application could itself figure out answers to all these questions and be able to assist the users in real time? Now, as we all know that web applications of today, they run in a sandboxed environment, and therefore they do not have access to all the privileged browser APIs, and therefore they cannot perform all such measurements. So it's only logical to reason that the browser can perform all such measurements because it runs with elevated privileges on the operating system, and therefore it can, once it has those measurements, it can provide the web application with these measurements and data in a secure and privacy-preserving manner. Now, this solution has two benefits. First, it relieves the end user of the burden of having to figure out answers to all such questions. And secondly, it will allow the developers to assist the end users in real time. Now, having convinced you of the merits of building a network measurement platform within a web browser, let's discuss Fathom's design. Now, like any other measurement platform, Fathom also has a set of design goals. We would like to perform a large variety of experiments, and so Fathom must have a rich set of measurement APIs. Also, Fathom's measurements should be accurate because inaccurate measurements are worthless. Now, because we are trying to build Fathom within a web browser, execution of Fathom or its APIs must not in any way degrade or lower the standards of security and privacy available to the end user as of today. Moreover, they should enhance the security and privacy of the end user when performing sensitive end host measurements. Further, because Fathom is built into the web browser, its execution must not hamper normal web browsing activities, so it should have low execution overhead. Next, Fathom should be portable so that it can be ported to a large number of end host devices for performing large-scale experiments. And lastly, Fathom should be easily extensible by both researchers and practitioners without having to worry about the technicalities of either Fathom or the web browser itself. Now, we surveyed the set of capabilities that we would desire in such a network measurement platform, and we classified them into 4 different categories, each forming a separate namespace in Fathom. Now, the first namespace is the socket namespace, which provides APIs for all low-level socket management operations. The second namespace is the proto namespace, and it contains APIs for implementing user-level protocols like DNS, MDNS, UPnP, and HTTP. The third namespace is the system namespace, which provides APIs for controlled access to system utilities like ping and traceroute. Now, this class of APIs are used when other Fathom APIs cannot be used for direct measurements. And lastly, we have the utils namespace. This namespace contains APIs that provide access to miscellaneous browser APIs, including timer and access to passively collected measurements. Now, this slide shows an example use of Fathom API. Now, assuming that we have to perform, say, a traceroute experiment from an end host to, say, Google Maps web server, we can make use of the traceroute API, which is part of the systems namespace. Now the traceroute API has two arguments. The first is the host to which we want to perform the traceroute experiment to, and the second is a callback function. Now once the results of the traceroute experiments are available, this callback would be invoked, which can further process the results. Now as we had seen in earlier slides, that Fathom APIs are powerful and they allow users to perform a wide variety of measurement tasks. So it's possible that there are some malicious scripts that might misuse Fathom APIs to launch, say, denial of service attacks on arbitrary end hosts, or even exfiltrate sensitive user information while performing measurements. So Fathom provides a five-fold defense mechanism to prevent such misuse of Fathom APIs. I'll now describe each of these defense mechanisms in detail. Now, the first defense mechanism is a client policy. When an end user installs a Fathom enhanced web browser, they can create a client policy. Now, basically, a client policy is a set of directives that instruct a Fathom to allow or to either allow or deny access to Fathom APIs for scripts from specified origins. For example, in this client policy, all scripts from the google.com domain will have access to the proto namespace, while say scripts from untrusted.com will not have access to the socket namespace because of these tags which says either allow API access or deny API access. Basically a set of either blacklists or whitelists for APIs. Now, no matter how exhaustive this client policy is, it's not possible that we can encompass all the domains. So it's very likely that, say, a user Alice visits foo.com, the website foo.com, which wants to access, say, Fathom APIs. Now it's likely that foo.com does not have an entry in the client policy. In this case, Fathom would simply launch a security dialog box saying that a web page is requesting Fathom privileges. Do you want to allow or deny? But as you can see in this dialog box, this is not informative at all. It does not give any indication to the end user about the nature of the script being used, or what is the set of resources that would be what would be the set of client resources that would be used when the script executes. So Fathom mandates the use of a script manifest. Now, a script manifest is basically a declaration of what resources would be used by the script, and this is made upfront. For example, now when Alice visits foo.com, now foo.com would respond with a measurement script which uses Fathom APIs, and along with it, it would also provide a script manifest. Now, a script manifest has two parts basically. First is the set of APIs, Fathom API namespaces that it wants to use, and the second is the set of cross-domain hosts that it wishes to communicate with. In this case, it wants to access the domain bar.com and on any specified port. Now, when Fathom sees such a script manifest, it parses the manifest and creates an updated security dialog box which provides information about the set of APIs that the script is going to use, and along with the hosts, cross-domain hosts, which the script can communicate with. And now the user can take an intelligent decision whether to allow or deny the script execution. But as you would be seeing here, that this security dialog box is good enough for, say, networking gurus or geeks. But average end users still find it hard to comprehend what's listed in a security dialog box. So we are still working on an intelligent and easy mechanism so as to allow end users to understand what can be the consequences of allowing such measurement. But this is a hard problem and we'll tackle it in future work. Now assume a case that there is an untrusted script running on an end host which wants to open a TCP connection to, say, a third-party server called bar.com. Now, how can bar.com prevent itself from unwanted cross-domain communication. So to tackle this problem, Fathom suggests the use of a server manifest. Now a server manifest is similar to the cross-domain.xml policy file which is available for Flash applications. Now in this case, when the script wants to open a TCP connection, Fathom would request the server for its manifest file, which is essentially a set of blacklists and whitelists. Like it would allow scripts to act for cross-domain, it would allow scripts to perform cross-domain activities, say for google.com, but it would disallow scripts from untrusted.com to perform any cross-domain activity. Now Fathom parses this set server manifest file and takes appropriate action. In this case, it assumes that Alice is part of untrusted.com and therefore it disallows the opening of the TCP connection. The last set of security mechanism is the code signing. Now when a user sees this security dialog box, he gets no indication about the trustworthiness of this script, whether it's coming from a legitimate source or say a malicious user who's trying to attack the network. And this is because it's very hard to reason about the trustworthiness of the script just based upon the origin of the script. So what Fathom provides is the use of signed scripts. This is very similar to the signed Java applets that are available these days. So what Fathom provides is a way to sign, it recommends that say researchers and practitioners can use signed scripts and which can contain say the name of the script as well as the name of the publisher, thereby allowing end users to reason about authorship instead of script origin. And reasoning about authorship is far easier and easy to do as compared to reasoning about the origin of the script. Now having seen the design of Fathom's API and the set of security mechanisms in place, let us take a look at how we can implement Fathom in a real-world web browser. Now in the context of the web browser, the design space for implementing Fathom is limited to 5 sets of technologies. The first is the standard web JavaScript, which executes in a sandbox environment within the web browser. And therefore it does not have access to all the rich browser APIs, and whatever APIs it has access to, they have low accuracy. But the one important advantage of using standard JavaScript is that it's portable across all different browsers and across all different operating systems as well. Next up, we have a JavaScript-based browser extension. Now, a JavaScript-based browser extension enhances the functionality of a normal web browser, and it runs with elevated privileges. Now, because of these elevated privileges, it has access to all the rich browser APIs which have good accuracy. I say good here because the accuracy depends upon the implementation of the API over here. Now, because different browsers have their different extension frameworks, a JavaScript-based browser extension written for one browser will not be applicable for another web browser. But a JavaScript-based browser extension will be portable across all the browsers for that particular web browser. Moving on, for runtime plugins like...
What do you mean by accuracy here for the browser?
The granularity of measurement.
Oh, I see.
Basically, that's the notion of accuracy here.
Is it also to have a high privilege, for example, for
yes.
changing UDP, IP packets?
We
cannot do it with the web JavaScript.
No, you cannot.
But with the extension.
You can, with the extension, as I'll tell you in the upcoming slides, that you have raw TCP and UDP access, but you cannot intercept incoming UDP streams or maybe modify packets. So runtime plugins like Java and Flash, they have access to rich browser APIs with high accuracy. But as mentioned in one of the earlier slides, the existence of these runtimes is not guaranteed on the end hosts, and therefore their portability is under question. A custom plugin is a piece of native code which enhances the functionality of a web browser, and it has access to all the rich browser APIs with high accuracy. But again, like extensions, one plugin framework is not compatible with another browser's plugin framework, and therefore a custom plugin for one browser will not work on another web browser. And because it's native code, it needs to be recompiled for all different operating systems, and therefore a custom plugin is not portable. Last up, we can take say an open source web browser, build all Fathom capability within it, in which case we'll have access to rich APIs. But this solution will not be portable because it requires end users to specifically install a new web browser, which has huge overheads. Now, based upon this design space that we observe here, we see that a JavaScript-based browser extension provides a sweet spot for implementing Fathom and all its capabilities. So we surveyed the set of popular web browsers and their extension frameworks, and we selected Firefox as a target platform. And basically for two reasons: because Firefox is a popular web browser, and secondly, it has a very rich extension API called Xtcom. Now we implemented Fathom as a JavaScript-based only browser extension, and therefore it's portable across all the platforms supported by Firefox, including the Android platform. Now at this point, I'd like to mention that Fathom is not specifically tied to Firefox. It can be implemented in any other web browser. We just selected Firefox for the ease of implementation for a prototype. Now this slide shows the schematic architecture of the Firefox web browser. Now the DOM subsystem is responsible for creating an intermediate representation of the web page, which is then rendered on the screen by the rendering engine. The JavaScript engine is responsible for executing all the JavaScript in a web page and any browser extension. The network engine implements protocols like HTTP, HTTPS, and FTP. And the network engine in turn uses a runtime library called NSPR for performing all low-level socket operations. The Xtcom subsystem is similar to Microsoft's COM system and is responsible for exporting rich functionality to privileged JavaScript. One of the key functionalities it exports is the JS ctypes module, which allows privileged JavaScript to access functions defined in runtime libraries like NSPR. Such functionality is not available to the standard web JavaScript. Now Fathom enhances the Firefox web browser at several levels, as shown here. Now based upon the functionality in Fathom, we can classify it into two parts. One is a front-end part and the other is a back-end. Now the front-end is responsible for creating a Fathom namespace in the global window object on each web page. Now once it has created this namespace, it attaches references to all the Fathom APIs to this Fathom namespace so that JavaScript on the web page can have access to Fathom APIs. The backend is actually responsible for implementing Fathom APIs and performing measurements. Now one of the key things that the backend must do is implement these APIs in an asynchronous manner. The browser's user interface and the extension's JavaScript, they share a single thread of execution, and any potentially blocking IO call made by the extension can render the browser unresponsive, and therefore it's imperative that all Fathom APIs are implemented in an asynchronous manner. Now let's see how Fathom performs in real world. Now Fathom performs passive measure, continuously monitors the end host and the web browser for performing passive measurements. Now it's very likely that simply the execution of Fathom might impose an overhead in normal web browsing. So in order to quantify such overhead, we selected a set of popular and complex web pages and determined their load time with and without Fathom. Now the first table in the column the first column in the table shows the set of benchmarks that we used. The second column shows the average load time for each of this benchmark in a normal web browser. The third column shows the average load time for each of these benchmarks in a browser enhanced with Fathom. And the last column shows the relative overheads for each of the benchmarks. Now across all these benchmarks, the average, the relative overhead is less than 3.2%, which is typically imperceptible to end users.
Sorry, I have a question on this. The test here is that you are running Fathom tests?
No, it's just loading of these web pages with Fathom running in the background to collect passive measurements.
Okay.
So we wanted to see how execution of Fathom, even passive execution of Fathom, can impact normal web browsing.
Okay, and it doesn't impact?
Yeah, it's just 3.2% across these complex web pages. Some of them are complex, some are popular web pages. And we found that the overhead incurred is typically...
but Fathom is doing nothing, I mean, why? When it is not analyzing?
It's performing passive measurements, like when the web page loads, it tries to figure out what was, say, the DNS resolution time, the TCP connect time, the time taken to load the web page, and it performs a host of measurements on the system, analyzing its CPU usage, memory usage, everything.
Just a question. This is with only one tab button. You use only one tab, then you don't use multiple tabs at the same time.
No, so for this experiment it's just one tab. For multiple tabs, I'll come in the coming evaluation further. Yeah, so for the next set of evaluation, we wanted to test the accuracy of Fathom's measurement, basically the timestamp generation and the accuracy of Fathom's measurement. Now, in order to perform these, so we performed these experiments under 3 different scenarios. First is a no browsing scenario where we just run the measurement script in the absence of any competing browsing activity. The second experiment scenario is a passive browsing scenario where we first load 4 complex web pages, and after the pages have been loaded, we run a measurement script. So the only competing activity here would be any asynchronous requests from the web pages, like loading of ads, etc. And the last experiment scenario is an active browsing scenario where we load the measurement script while simultaneously loading 4 complex web pages. For the timestamp accuracy experiment, we send a train of 106 probe packets between a client and a server, and each probe packet is 200 bytes long. We then observe the send and the receive timestamps on the client using both Fathom and TCP dump. And to get a measure of accuracy, we measure the difference between the 2 pairs of timestamps. That is, we measure the difference between the send timestamp as observed on Fathom and TCP dump, and similarly we obtain a difference between the receive timestamp between Fathom and TCP dump on the client side. Now this table shows the results of our experiments, and it shows that under normal operating conditions, Fathom's timestamp accuracy is 1 millisecond, which is the available granularity of the JavaScript timer on the web browser. Now, as we increase the amount of cross traffic on the host, which can happen if we have multiple tabs, say 40 or 50 tabs open at the same time, then this accuracy degrades. And in order to assist the web developers or experimenters so that they can tune their scripts, we provide an API called fathom.utils.metrics, which allows them to figure out the amount of cross traffic when the script is executing.
Sorry. Here the cross traffic is always from the browser, right? So you're not measuring any external.
External as well.
External as well.
Yeah.
So you can also know whether you're doing upload to Picasa.
Yeah.
And in this case, what would be the accuracy? I mean, it remains under 1 millisecond, or
Which one?
if you have external activities, you say that the accuracy degrades, or even if you have multiple open tabs.
The accuracy will degrade.
Yeah, but how much?
It depends on the amount of cross traffic. So in our experiments, we had In the extreme case for active browsing where we had multiple tabs open, it went down as much as say 30 milliseconds or even further. It just depends upon the amount of cross traffic we have. Under our experiment scenarios, it was pretty bad.
Yeah, because it's in your experiment. I mean, because I mean, you just set an overview, like it's a passive measurement. I guess you deal with the timestamps, etc. So that occurs for all the open webs. That's the purpose. That Fathom cannot target a specific tab, for example.
Yeah, Fathom can target in fact specific tabs as well. But this timestamp accuracy is done when we say load a measurement script while simultaneously loading other web pages as well. The passive measurement happens for each web page, and that is even if we don't have any measurement script, Fathom continuously monitors each web page. So the timestamp accuracy over here specifically demonstrates that if we have a measurement script which is loaded under different browsing scenarios, what will be the impact on the measurement script, or the timestamp as generated by the measurement script. Because this measurement script runs like standard JavaScript, whereas Fathom runs in a privileged mode. So there is a difference in the browsing contexts here. Sure. To determine the timer accuracy available for Fathom experiments, we perform an experiment where we send 51 probe trains of 100 probe packets each between a client and a server. Each probe packet is 200 bytes long and it's fired at an interval of 200 milliseconds each. Now the aim of the experiment is to determine how is this precision, how is this timer precision affected as we increase the amount of cross traffic on the host. And we observe that with the increase of any concurrent browsing activity, which might include number of different tabs or even passive or even say cross traffic on the host, this 200 millisecond precision degrades fairly quickly. And the reason for this is that if we open a number of tabs in a single browser window, they all share the same runtime. And on increasing the number of tabs, we increase the number of internal browser events that are generated for each tab. Now, as we increase the number of internal browser events, they hamper with the firing of this JavaScript timer. And therefore, this accuracy degrades. Now, in order to assist the developers, we suggest that they can make use of the JavaScript's built-in date API, which checks for the wall clock time. Now, experimenters can use this date API to figure out whether the timer has fired on time or it was delayed. We'll also perform 3 case studies with Fathom. And the first case study we did was to implement several key tests from the popular Netliner test suite. Now, the aim of the study was to demonstrate that researchers can use Fathom APIs to build complex toolkits, and definitely Fathom-powered Netliner confirms its versatility. In the second case study, we built an application to check for web access failure, and the motivation for the study was to build it as an incentive for end users to install Fathom in the first place. Now, we observed that there are several network measurement toolkits which require network connectivity as a prerequisite. In the absence of network connectivity, these toolkits simply fail. So we built an application called Debug My Connection, which uses Fathom APIs and performs several passive and active measurements and informs the user if he has any network connectivity or not. The last case study was a web services debugging case study. Now, the aim here was to show that web developers can use Fathom APIs to assist end users. And for this case study, we played the role of the Google Maps web developer, and we wrote diagnostic scripts which can pinpoint the cause of, say, a slow loading of Google Maps web application in real time. I'll now demonstrate 2 of our case studies. So, in the first case study would be I'll go to our Fathom web application, which is located at fathom.xc.berkeley.edu, and start the analysis. Now, as shown in one of the earlier slides, whenever a script starts, Fathom mandates that it should use a script manifest. And the script manifest located at this web application makes use of all the 4 Fathom namespaces, but it does not communicate with any other host in a cross-domain fashion. So on allowing this script, it performs several tests like access, link, latency, upstream and downstream bandwidth measurements, UDP and TCP, port reachability, HTTP functionality like checking of proxies, DNS functionality and correctness. Now, one of the key things that we observed while implementing these tests was that unlike standard Netliner tests which are implemented in synchronous Java, implementing tests in Fathom powered Netliner required us to chain together a sequence of separate actions. And this is really because of the asynchronous nature of Fathom APIs. The other thing that we observed was that the total number of, say, the ballpark lines of code required to implement tests in a Fathom Netliner was similar to the standard Netliner tests. So there is no real extra overhead of implementation except for the fact that we have to take care of the asynchronous nature of Fathom APIs. Okay, I'm not sure what happened.
The network is a bit slow, perhaps.
Yeah.
And this is a client server.
Okay, let me just refresh this again because it shouldn't be. Okay. Okay, we can let it run in the background.
And for instance, could you do a ping or a trace route with Fathom? Because there is a trace route functionality.
Okay, so we can see it over here. So, moving on to the second case study that we have is the debug my connection capability, which we can exercise right here. So when the user installs the Fathom extension, he gets this icon on the toolbar associated with the menu. On running this capability, we run 4 classes of tests. Let me see. So the first is basically the general connectivity, where we check for the available interfaces on the system. What is the configuration, the set of IP addresses, whether they are associated or not. The second is the network level test, where we inspect the routing table and run a traceroute to our echo server. So we can see the traceroute summary in JSON format. So it reached icir.org. So yeah, so it should have worked. I don't know. Okay.
Yeah, but you don't run a trace route from the client. I mean, because you don't receive ICMP. Yeah, but you connect to an echo server. So that's the echo server that trace route you, not you that.
Yeah, so this is from the client basically. Yeah. The third test that we do is we use Fathom APIs to implement. We check for a configured DNS host, and then use Fathom DNS APIs to resolve a standard name, which is google.com here. We then use Fathom APIs, Fathom's HTTP API, to retrieve a HTTP entity body for standard host, which is google.com. Now, apart from these active measurements, we also perform a set of passive measurements, which is like we analyze the number of system tasks, the amount of CPU usage. Forgive me for the incorrect, for the bad graphs over here, but then we have the memory usage, used and free, the network traffic, the amount of HTTP traffic as observed by Fathom, the Wi-Fi connectivity, link, signal, and noise, and lastly, the browser's memory usage itself. Now, in the extreme case, okay, this is stuck, maybe I'll come back to this later. Now, in the extreme case of, say, no network connectivity, which I can do by disabling the network interfaces on my computer here, So I'm like disconnected now. So, okay, where's my mouse? So in this case, if I run debug my connection, what I should expect to see is all the tests have failed here. So if I run, so all my general connectivity and network level tests have failed, and so will the DNS and the HTTP tests.
It's pretty fast. It is pretty fast.
Yeah, thank you. But I'm still concerned about why that didn't work out.
You have to check it.
Oh, okay, I forgot to. Okay.
Now it's clearly not.
Yeah, okay, I'm just resuming that. Okay, so I'll show that demo later. But moving on, to conclude, we've seen that Fathom is a practical browser-based network measurement platform which provides a programmable interface for writing and launching measurements. We have a prototype for Fathom for the Firefox web browser which incurs a modest overhead with acceptable accuracy. And Fathom has several built-in checks to ensure user security and privacy when performing measurements at the end host. And you can download and play with Fathom at http://fathom.xc.berkeley.edu. And we welcome all feedback. If you want to contribute with code, please contact us, don't hesitate. And thank you for your attention.
Well, a couple of questions, if you can hear me.
Yeah,
So one is, have you got something dangerous like a Fathom console in your Firefox? So can you write some code down, like scripts, on the fly? So before somebody will try to ask you, can you ping something from a Firefox
I don't
console?
have a system, so but basically you can, if you have Fathom installed, then you can write web pages where you use Fathom APIs.
No, I see.
And this is a JavaScript? It's a
Yeah,
Fathom.js?
this is all JavaScript, yeah.
And that's it.
I can show you examples of web pages that we have written for. Let me just run it once. Okay, I'll now show you some sample web pages that I have already written. For example, say for example a UDP connectivity. So what you can do is just have a script which declares a manifest, and then basically where you use Fathom APIs is you open a UDP socket and then you pass in a callback function, which is this, which has another callback function which uses a timer here. It uses a callback function called send, which actually sends the data. So you can just chain together a sequence of Fathom APIs to perform.
You have a receive? So you
Yeah, we have a receive as well.
So how can you can't receive ICMP?
So the browser works at the application level, and the Fathom APIs that we have, they are only limited to raw TCP and UDP. We cannot go we cannot work with ICMP.
I see.
Yeah, that's why we couldn't implement our own trace routes.
Yeah.
And ping, etc.
That's why we call the system
System you can-
trace route.
Yeah.
From the system you get the raw ICMP packet.
Uh,
So what would you get from when you call the
No,
system?
so when we call the system, we call ping.
Okay, so
you can do
a
record.
So the ping command has
Okay.
the right access, but we don't.
But you can have a record route, for example.
But in this case, in the callback, what you receive is the output of the ping command.
Yeah.
And so, can you go back to the conclusion? Because I disagree.
Okay.
No, but I'm joking. So, now here you said that you got low runtime overhead, but basically before you shown that for each tab you open, you have a fixed overhead. Meaning that the overhead may be linear in the number of tabs you open. Is it true or not?
We haven't performed a large-scale case study. We just did 8 popular benchmarks,
Well,
popular
like,
benchmarks.
if you go to the slide where you have all the benchmarks, and imagine that you open a browser,
Yeah.
This one, and you open all these different things in the tab. So would the overhead remain 3.2%, or would it be the sum of those?
It should not be the sum of the all those, because when the browser loads several web pages, many of the phases of the rendering process and the parsing process, they are overlapped. So we will not see a sum of them, but it will definitely be about the same ballpark. It will definitely not be the sum of all that.
Is you say that you're not going to do more action, so Fathom is not going to do more action for each of the page.
Yeah, but
because the overhead is associated with the fact that it's, say, monitoring the system, and it will monitor the system irrespective of the 1, 2, or n tabs. So the number of action that is doing.
The work that Fathom does is usually it gets masked by say network latency and the time that browser takes to render a page. So Fathom's actual work, it gets masked. So it's not additive in nature. There will definitely be an increase in the overhead, but it will not be additive.
If you do a per connection, any kind of things per connection, per HTTP connection, it's definitely additive. So we mask for each page, but the number of things that you will do increases linearly with the number of things that you treat.
No, but the browser has several different processes that go on. One is JavaScript execution, the other is CSS parsing, HTML parsing, and then rendering. The work that Fathom does, it's get masked by the other processes, so you will not see an additive increase. Or things get masked. That's the point.
Yeah. Okay.
I have a couple of questions. So the scripts can be called by iframe. So for example, if I have I don't know, an ad which asks for access to Fathom, and I granted an access to the domain from which the ad is loaded,
yeah,
could it access to the iframe even if it's just a third party, it's not the first party?
Yeah. So the Fathom namespace gets attached to the window object. Now each iframe also has a window object. So each ad, if it runs within an iframe, can also have access to the Fathom APIs. But the user has to, the first thing is that it should have a script manifest, which the user must explicitly allow, or it should have a client policy.
But the manifest doesn't tell when how often the domain can run tests from my browser actually.
No,
so if, for example, I agree that Facebook can check, can do measurement from my browser when I'm visiting Facebook, but then also with the social plugins you can do that every time I visit a web page where I have a social plugin.
Yeah.
And do they also have access to memory? Like, because in one of the windows it shows that they can see the memory consumption.
We have access to two kinds of information. One is the one is the Firefox memory consumption, and the other is the system's memory usage, which we get by invoking the top utility. So you can get you can also get a per process usage.
Because I'm asking that because there was a paper at Open this year, and they show that on Android you can guess what has been visited by a browser. What are the page visited by a browser just based on the memory footprint that you have. So if you can have like a real, I don't know, if for example I have a tab open and then there is Facebook widget, and then they have access to my memory consumption, they can infer what I'm visiting on the other tabs, and that might be an issue. So maybe you want to restrict access to this system utility because it's quite critical.
So we don't have access to the memory footprint over here. All we know is the amount of memory used. We don't have access to the raw memory.
Well,
I know what about the paper you're talking about. Over there, they were talking about the system memory, if you can figure out at the process level. But over here, we don't have access to, say, memory used per tab.
But, okay.
It's at a process level and at a system level. So for the process level, we have it for Firefox, and at a system level, we have it for everything.
Okay. One last question, just for curiosity. Did you use Jetpack for the extension or experiment?
The Jetpack, unfortunately, cannot be used for implementing this. It's very restrictive in nature. So we implemented much of it in the legacy format. So yeah.
Because it will be much easier. I know it's missing some API, but it will be much easier, I guess, to try and support it on Chrome and Safari.
So one reason for not using Jetpack is that it's still not stable. They claim certain security features which are still not implemented yet.
Okay.
So one of the reasons was that.
Can you go back to slide 18?
Slide 18, okay.
Which is something like server manifest, if I recall correctly. Okay, so here what you want is to prevent distributed denial of service attack from user to servers. So
Yeah.
one of the use cases of this. But how can the guy, allow access from, so if you want to let user perform measurement, typically you will want to allow everybody, if you're a measurement server, right? So can you differentiate from users coming from different domain? I do not see, so here is the user domain name, or is the...
It's a user domain.
Yeah, so it's not even the what kind of plugin you would like the user to run on your server. It's not that this is the example bar.
Yeah, this is a third-party server.
Which
so
is accessed by foo, okay?
So a foo.com sends in the
Okay.
measurement script,
Exactly.
which goes to Alice. Now, it requires access to, say, a third-party server, which is bar.
Okay, exactly. So
Yeah.
what I mean is that bar could allow easily foo or another measurement script made by Google to access the server.
Yeah.
But it doesn't know what user is going to install it kind of thing. So it probably is going to write that it allows access from any IPs, provided that the ISP is using a plugin that is provided by the domain foo.com, for instance. Isn't this something feasible in your framework? So authorizing the server to be accessed from only some plugin. So exactly like the user authentified the writer of the plugin, here the server is authentifying or allowing some user, but he has no clue what is the IP or the domain of the user that is going to contact him. Right? So
Identifying a plugin is hard because users can, because it's an extension, it's open source, so users can tweak their extensions. It has to be certified.
Signed plugins like you were showing before.
And those were signed scripts.
Okay, so, or signed scripts. Sorry.
Yeah.
I used the wrong word.
Okay. So
But I guess that signed script it can be identified. Whatever here, I cannot see really how a server can use this kind of manifest file.
now, in case of a signed script, we still want the discretion of allowing a cross-domain communication to be left to bar.com. If bar.com does not want scripts to be executed or incoming connections from a particular domain, we don't want that. Signed scripts, definitely, if bar.com accepts all signed scripts, say from foo.com, then that is one criterion. But there is another overriding criterion over here that bar.com does not want access, cross-domain access from any untrusted IP one. Because they might be, say, in a global blacklist.
A priori, this is going to be any kind of user running Fathom, right? So a priori, the sitbar.com is going to be contacted by any guy who has installed a plugin by foo, and the bar.com domain doesn't know who has installed that. So how can he provide whitelisting, blacklisting?
No. So every time this connection is being made, the first thing that happens, so if a script wants to open a connection, the first thing would be to fetch.
No, this I get, but I don't get how the server can write useful information inside the manifest.
So it can be based upon, this blacklist and whitelist can be based upon any global list available. It need not be very specific to Alice in particular. It can be, say, a block of IPs or a set of arbitrary domain names that there are available on the internet. Say, if one has a knowledge about, say, which bot has infected a set of IPs, I can just put them in this block so that they are not able to use Fathom APIs anymore.
Okay, I don't see a use case of this specific server manifest.
Now let me just check if I have this.
And I know I'm a pain in the neck, sorry.
It's still stuck. I don't know why, but this used to work right before.
It could have been interesting to do a ping from here, for example.
Maybe I'll just.
Are there any use case where you could, well, where a third party would be interested in using that because, or an active tab, like something, a tab in the background? Do you see any practical use case for that, or because you could, I think, easily disable that from your script? You could
Background tab using Fathom API?
Yeah, or even third party using Fathom API.
So for third parties, we don't have any restriction as long as the user gives explicit consent, either in the form of a dialog box.
But does he really realize that it's also for third party? Because when you go on Facebook, it's a first party and you give your consent to Facebook because it's there. But when it's a third party, I'm not sure that they realize that it's still has access to the same API. Even in third party context, you could have something in your policy say, okay, I grant access to Facebook only when it's a first party.
We don't have that level of granularity in our policies right now, but certainly that can be worked in. And as for your case of background tabs, we do allow experiments to run in the background because we want long-running experiments to work. But there are certain browser features, like Firefox clamps the timer for any experiment running in a background tab. So the user must, so either the user should change the preferences of the browser, or the user must explicitly check whether the timer matches the wall clock time or not. So there are certain issues with the browser's background tab. The other thing that we could do is we can, instead of running the script on a web page, we can give the entire script to Fathom to run it in the background. So instead of being a background page, it will now become a background task. In that case, we'll have all the accuracy and precision what Fathom can provide. So you can still have long-running measurements working.
3 o'clock.
Okay.
So then.
Okay, let me just do one more.